All right, let's start then. Hi everyone, I'm Surbi and I'll be taking today's recitation. The topic is graphical models and I'll be covering BaseNet and deseparation majorly. So let's get started with this. So graphical models, the key ideas or the key idea or the need for graphical models will be explained in this slide. If you remember, most of the algorithms that we did so far in machine learning class have been majorly based on the conditional independence assumption. Most importantly, naive Bayes relies on the conditional independence assumption. If you remember, the final form of the expression for naive Bayes comes from conditional independence, where you see that the random variables are considered to be conditionally independent of one another, and that's how you get the final expression for naive Bayes. Now, it would be nice if we get some sort of mechanism to visualize the conditional independence of one variable over another. And that's where graphical models come into picture. So this provides a means of visualizing the entire scenario where one variable would be independent of another or may not be independent of one another. So that's why we deal with graphical models. And the two major types of graphical models would be directed graphs, that's also known as Bayesian network or BaseNet for like a shorthand notation. And so 10601 would be covering BaseNet. And then there's also undirected graphs like Markov hidden models, Markov random fields, and those would be covered in other classes. But let's just focus on BaseNet for the time being. So any questions on the need for graphical models or any other doubt regarding conditional independence? I think by now we've seen lots of algorithms which deal with conditional independence, so it should be pretty clear. So let's just see why and how graphical models will help us. So it's been really popular over the last few decades, and it allows us to visualize the joint distribution of variables, the priors, the posteriors, the likelihood. Everything becomes really visible and clear in graphical models. And as you can see, it's useful in the real world as well, where for diagnosis, help systems, text analysis, and those other machine learning applications. Let's just quickly brush up on conditional independence. So by definition, a variable x is said to be conditionally independent of y given z if the probability distribution governing x is independent of the value of y given the value of z. This can be expressed as if if x is conditionally independent of y given z, you can write the left-hand side, just get rid of the y term and write it in the form of x and z. So that's going to be probability of x given z. So you just get rid of the y term. You can also reverse it. So if y were conditionally independent of z, given x. So it would be, so you can just get rid of the z term and then write it as p of y given x. So the statement is important, and then you can just derive the final expression. And for example, when you consider thunder, rain, and lightning, so you can see the LHS. It says that thunder given rain and lightning, this can be written as probability of thunder given lightning because thunder is conditionally independent of rain. Is that clear? So there's another term that's known as marginal independence. It's slightly different from the conditional independence term. So what happens here is when x is marginally independent of y, this means that the value of x and y, the probabilities of x and y do not affect one another's probability, and the final joint distribution for x and y can be expressed as the product of the two probabilities. So that would be probability of x, y will be equal to the product of the probability of x and probability of y. This can also be written in the form of p of x given y. You get rid of the y term because x is marginally independent of y. Get rid of the y term, and the RHS is just p of x. So this is marginal independence, and this would help us in graphical models. So when you want to infer something from the graphical models, conditional independence and marginal independence terms would be very relevant, and you would keep seeing when you start solving questions on it. So any questions on conditional independence or marginal independence? So for marginal independence, you can just say that the probability, the joint probability, is nothing but the product of all the probabilities. Let's also review some useful terms which would help us with graphical models. So if you consider a probabilistic model, it has some random variables x1 to xn and theta 1 to theta n. And we want to find the joint probability distribution for this. The joint probability distribution can be just expressed as the probability over all the random variables. So that would be probability over x1, x2, xn, and theta 1, theta 2, theta n. So that's joint probability. Now say out of these random variables, x1 till xn are observed. So we know the values or we know the probabilities of these events. So we can also, from this observation, we can derive other terms. So from this observation, we can say that the prior term would be the probability of the unobserved variables. That's going to be probability over theta 1 to theta n. So probability over unobserved variables would indicate prior. Now, what's a likelihood? As you can recall, likelihood would be probability of observed given unobserved. So that's going to be probability of x1 till xn given theta 1 to theta n. So that's likelihood, observed given unobserved. Similarly, posterior would be probability of unobserved given the observed terms. So that's probability of theta 1, theta n given x1 till xn. So these are the terms which would come handy later on. Any questions on this? Do you want me to repeat this? I can repeat again. Okay. So x1 till xn are observed terms, theta 1 and theta n are unobserved terms. The joint distribution is probability over all the random variables. Prior would be the probability over unobserved terms. Likelihood would be the probability of observed given unobserved, and posterior would be probability of unobserved given the observed variables. Okay. Now let's start with BaseNet or Bayesian networks. So what a BaseNet signifies is it's just a visual graphical structure which would give you some idea of the conditional independence of variables over one another. So it's just an expression or a graphical structure for the joint probability distribution. As you can see, there's a tiny example which I'll elaborate later on. That's like a general form for BaseNet. So there'll be nodes, there are going to be nodes, there are going to be edges. Each node will represent a particular random variable, and the edges will determine the dependency of one node over another. And for each node, you can see the conditional probability distribution, which will be given by P of X given probability of some other variable. So say if, I'll just quickly go through an example. Yeah. So say for this particular BaseNet, so we have some random variables: storm clouds, lightning, rain, thunder, windsurf, and the arrows represent which variable depends on the other variable. From here, you can infer lightning and rain depends on storm clouds. Thunder, windsurf, they depend on lightning. Windsurf also depends on rain. So this gives you a general idea of how one node depends on another. And if there's no connection between any nodes, can you infer that it's conditionally independent? May or may not. So there are some rules. So if there's no edge connecting one node to another, then you can say that it's not conditionally independent because there's no path to go from one node to another. Okay? So so is windsurf conditionally independent of storm clouds? No, because there's a path from storm clouds to windsurf. So you cannot say that windsurf is conditionally independent of storm clouds. So one key thing to keep in mind is if there's a path which exists from one node to another, then it is conditionally independent. If there's no such path, then it's not conditionally independent.
Given probability of windsurf given rain, it is
independent of. Yeah, I'll come to that as well. So this is when none of the events are observed. When a particular event is observed, the rules change. We'll see that. So we'll see that in examples also. Some slides. Like I said, BaseNet defines the joint probability distribution in a graphical format. And if you recall, joint probability is nothing but probability over all the random variables. So if you take the probability of some random variables from x1 till x8, you can look at the BaseNet structure and just write down the probability distribution. So if you see, x1 does not depend on anything. X2 doesn't depend on anything. X3 depends on X1. So what happens is BaseNet gives you a very good means to break down the probability distribution. Now see, here are 8 terms. So if you go through each and every probability, you'll get around 2 to the 8 combinations. You'll have to see 256 probabilities. BaseNet breaks this down to only a couple of handful of probabilities. So it's reduced the computation from 256 to just these few probabilities. That's like one advantage. So what happens is you're representing the full joint distribution in some fewer parameters, and then you have, you know, which variables could be observed and unobserved, and then accordingly you can infer certain details from the BaseNet structure. We've seen this. And how do you construct a BaseNet algorithm? You'll just start with the random variables, pick one as the root node, and then depending on, so you have the final joint probability distribution. Depending on the relationship between nodes, you can draw a BaseNet structure. Let's see a quick example on this. This is an easy example. Say we have 5 random variables. A is Bernoulli, B is also Bernoulli, so the probability of each is going to be half. Suppose C is a sum of A and B. D is also Bernoulli, and E is sum of C and D. In this case, C and E are observed. Can you make a BaseNet structure on this information? You can start drawing. Like it's easy. So let's start. So we have an event A. A doesn't depend on anything. We have an event B. B does not depend on any other event. We have C. Now C is the sum of A and B. So C depends on A and depends on B. Right? Then D and E. And E is sum of C and D. So depending on what information is provided, you can draw a BaseNet structure. They also say that C and E are observed. So let me show you this. So C and E are observed. So you have the graphical model or the BaseNet structure. And so for this example, what would be the joint probability distribution? Joint probability is the probability over all random variables. So that's simply going to be probability of A, B, C, D, and E. Right? Now look at this. What can you say? This can be broken down into probability of A, probability of B, probability of C given A, B, probability of B, probability of E. E depends on C and D. So for these 5 variables, without the BaseNet, you would have seen around 2 to the 5 probabilities. Now this just breaks down into what, 6 terms. Okay, what would be the prior? Yeah. Remember, we just went through the slide. Prior, it's the probability over the unobserved variables. So the unobserved variables here are A, B, and D. So the prior would be probability of ABP. Okay. What would be the likelihood for this example? observed over unobserved. So CE, CE given ABD. And the posterior would be just reverse for this. So that's going to be probability of ABD given CE. Okay. We'll also see how, knowing that these two variables are observed, how we can make certain other inferences from the Bayesian structure. For that, let's just see what deseparation can tell us. So what does deseparation imply? So we have, say, three random variables x, y, z, and x and y are known to be conditionally independent of z. Now this will occur if and only if x and y are deseparated by z. What does that mean? So if there is a path which blocks the two variables completely, like consider x, can you see this? I'll just, so x, y, if there is no other, if there's no path or the path is blocked, this means x and y are deseparated. Since z is a variable which blocks the path between x and y, then it's known to be deseparated.
And the path is blocked by an observed, or even if we don't have if it's not an observed.
Yeah,
will
I'll
still
come to
be
that.
okay.
I'll come to that soon. So I'll give you a really nice thumb rule to remember. Yeah.
Should the prior be P of x, a, comma x, b, comma x, b? If a, b, d are the states,
Yeah.
the prior is over the observations, right?
Yeah.
So,
No, prior is over the unobserved. The prior is the probability distribution over the unobserved.
oh, sorry. But here a, b, d are the states and not the observation.
So all these nodes are just random variables.
Yes.
Yeah. So ABD are unobserved in this case. The shaded ones are observed and ABD are unobserved yet.
Shouldn't the prior be over the observed? I mean, am I missing something?
You don't know the probabilities for ABD yet.
Yes.
But you know XY and sorry, C and E. So ABD is over unobserved, like ABD are unobserved, and the probability distribution over unobserved variables would be the prior. I'm sure. Any other questions? Okay, so going back to deseparation. So if a path between two random variables is completely blocked, then you can say they are deseparated, which implies that they are conditionally independent. Now I'll give you a quick thumb rule how to go about with observed. Okay. So this thumb rule is known as the baseball game or whatever you can call it, baseball. So if you remember the structure that we had for A, B, C, D, and E. Okay. So if, say, you place a ball at one node, now if there's a path through which the ball can be thrown to some other node, in that case, if a path exists, then there's a dependency relationship between those two nodes. No, those two nodes. If a path doesn't exist, then there's conditional independence. Okay? So let's see what are the rules for this. So say you have one node and it's an unobserved node. And say the edges are in this form. So there's an incoming edge and an outgoing edge, and two incoming edges and two outgoing edges. Let's do this outgoing first for the time. So these are the three possibilities for dependency, and it's an unobserved node. So if the node is unobserved and there are incoming or outgoing arrows, sorry, one incoming, one outgoing, and two outgoing arrows, then a path exists. The path exists if the node is unobserved. But if you have this scenario, case 3, where there's one incoming node, sorry, incoming nodes from both the ends, the path would not exist. Okay? This was for unobserved nodes. For observed, for the observed case, the entire thing is the opposite for unobserved. So for the first case, where you have one incoming and one outgoing arrow, the path does not exist. So it's totally the opposite of what we had seen in this case. Similarly, two outgoing arrows, path does not exist. And these are observed. In this case, if the node is observed and the two arrows or the edges are incoming, then a path will exist. Either way. So this is like a thumb rule, and using these rules, you can make inferences from the base net. So looking at this structure, and now we know the rules of the game, what can you say about A and B? Is A conditionally independent of B? Let's see. So C is observed. Is there a path between A, C, B? Now this is like the third case. There's a path. So A is conditionally independent of B.
Oh, so if there is a path,
And the node is observed.
yeah, if there is the path, then there is a conditional
Independence. Yeah.
Oh, I thought it's the other way.
Oh, I'm so sorry. Yeah. Sorry. They're conditionally dependent. Yeah. You're right. I'm so sorry about that. Yeah. So if there's a path, they're dependent. Yeah. I'm sorry about that.
One last thing for the direction of the path for the unobserved. Here you have the observed and unobserved and observed.
Yeah.
And then you have the path, the direction of the path. The dot.
Yeah.
Here. No, the other.
This
Yes.
one?
Yes.
Yeah.
For the first and second cases,
Yeah.
you have this dashed line. You know that direction.
Yeah. It's like you can go in
both
either
ways?
direction. Yeah.
Okay.
So
Okay.
this just implies that there's a path and you can go either way.
Oh, I thought
Yeah.
that's okay. Thank you.
Even here, yeah, you can go either way.
Okay, thank you.
So when you're seeing this arrows in the form of a U-turn, that's when the path doesn't exist.
Thank you.
Let's see. The relationship between A and D. A and D, C and E are observed in this case. Now, this is an observed variable, and this is like this case. Sorry, the first case. So C is observed. So the ball cannot be thrown from A to E, right? Can the ball be thrown from A to E? No. So we cannot take this path. Is there any other path to go from A to D? C, D? No. So A is conditionally independent of D. So this is like a simple rule. If you just remember these two cases, I think that should be good enough. And once you know the dependency of one variable on another, and then you know which events are observed, you can quickly make inferences. And then you can write this in the form of the probability distribution and then solve the entire thing. So that will be so now in this case, if you can just see if C and A are conditionally independent. If yes, you can replace this entire term with C given B. For this, you can just refer to these rules and see, and even this term can be simplified in the same form. Does that make sense? Okay. So this sums up base net as well as the d-separation. And I think you should be able to solve similar questions in the homework as well.
Can you explain that? How could you simplify P
Yeah.
given A and B to P
Yeah.
given B?
So do you remember this definition of conditional independence? Yeah. So remember this definition, we said that if x is known to be conditionally independent of y given z, in that case you can just replace the y term, you can get rid of the y term and write p of x given y comma z as p of x given z. So this comes from the conditional independence definition itself. Now, when you see the graphical model or the Bayes-Net model, you simplify the joint distribution into fewer parameters. Moreover, you can replace these parameters depending on the dependencies and replace them with simpler parameters again.
So, I'm sorry. But that means that A and B are independent, right? That's why you are.
For this, you have to see the dependency between x, c, and a.
C and
And
A.
a. Okay, let's just see that. There is a path. It's not conditionally dependent, so you cannot replace this. Okay, let's see the other term. So that's P of E given C and B. E and C. There is a path. Well, you cannot. But I think for the cases where you have a comparatively higher number of nodes, you can simply look at the graphical structure, apply these rules, and you can simplify those terms which actually comply by these rules. Any other questions? Okay, so this sums up baseball and Bayesian networks, as well as the concept of d-separation. So yeah, that's all I have for today. If you have any questions, I'll just hang around. And yeah, thanks for coming. Like only 5 people.